All right, so we're going to start out by finishing up section 3.1. And we're going to look at 6 different formulas. Okay, 2 for sine, 2 for cosine, 2 for tangent. I'm going to put a number next to the formula just to name it. It's not important just for us to discuss it in class, so we don't have to say this all out. We can just say formula 2a. Okay, but you don't have to know 2a for the test. Okay, what this formula is saying is that if you take the inverse sine of the sine of x, inverse sine and regular sine will cancel each other out. And the answer that you get is basically whatever you start with. But x has to be between 2 certain values. Okay, and we went over this restriction yesterday. Anybody remember what we said for inverse sine the restriction was? The angle had to be between 2 numbers.
Negative 90 and 90.
Yep, between negative 90 and positive 90. So this formula will work as long as you pick a value for x that's between negative 90 and positive 90. Or in radians, you're doing negative pi over 2 to positive pi over 2. And you can equal the endpoints. You can go right up to and include 90 and negative 90. Let's look at an example. Let's do the inverse sine of the sine of, I'm just going to pick a number between negative 90 and 90, 52. Okay, if I hit enter, what should I get based on that formula?
52.
I should get 52. The answer should be whatever you plug in for x. Okay, and it is. Okay, so I picked a number between negative 90 and 90. Let's pick a number not between negative 90 and 90. Let's do like 120. When I press enter this time, am I going to get 120? No. I get an answer, but I don't get back what I started with. That's because I didn't go between negative 90 and 90. Okay, any question on that formula? Okay, so all these formulas today, they're only going to work over certain intervals. Most of the intervals you already know. Okay, our last formula for sine is formula 2b. It looks similar to 2a, but there's an important difference. Anybody see the difference between formula 2a and 2b? Emma?
The inverse and the regular sine switch.
Yeah, in 2b, the inverse trig function went to the inside. In 2a, it was on the outside. This also has a restriction. Okay, but the restriction on this one has to do more with the picture of sine. Okay, and what it has to do with is how high and how low it goes. So let's look at the picture of sine. Okay, each mark there is on the height is 1 unit. So it's going by ones. What is the highest it looks like that graph goes? The highest, so 4 would be right at the very top. 1, 2, 3, 4. It looks like the graph, that wave reaches a height of 4. Yeah, it only reaches a height of 1. Okay, how about the lowest? Negative 1. Okay, so we always have to be between 1 and negative 1.
For this formula.
For that formula, yep. And I'll show you an example. Okay, I won't go through the example for every single formula, but just the first couple. Let's try the sine of inverse sine. Somebody give me a value here that would work.
0.
0. Okay, we could do 0. When I hit enter, what should I get? 0. And I do. The reason that value worked is because it was between negative 1 and 1. And remember, you don't have to stick with just integers. You could do like 0.37. That would work too. Any number between negative 1 and 1. Okay, how about a number not between negative 1 and 1? Just keep it simple. Sure, 2. If we try 2, and I hit enter, I don't even get back a different number that I started with. I get back an error. And it says that I tried to plug in something that's not in the domain, basically. Okay, so what we're trying to do in this problem, graphically, you're trying to find where that horizontal line and where the blue wave intersect. Okay, where do they intersect? Nowhere. They don't. That's why when you tried to type in what we had on the other screen right there, you can't do it. Okay. Graphically, that's why you can't do it. Let's look at some examples. Okay, so the kind of examples you're going to have with these formulas is basically like a true-false or a yes-no. So they'll give you an equation. Is the inverse sine of the sine of pi over 8 equal to pi over 8? And the answer is either yes or no. Okay, first thing we want to do is figure out which formula we have. So you got the inverse on the outside, regular sign on the inside.
This would be yes.
So is that 2a or 2b?
It's 2a.
Yep, that's going to be formula 2a. And did you say you think it's going to be yes? Yeah. Okay. We're asking, is pi over 8, does that fall between negative pi over 2 and positive pi over 2? Sure. Okay. Pi over 8 is a lot smaller than pi divided by 2. It's definitely smaller. Think of dividing pi by 8 and then dividing it in half. Right? It's smaller. So this is true. So we write yes. The next one says, is the inverse sine of the sine of 3 pi over 2 equal to 3 pi over 2? Okay, first, what formula are we using this time? 2a or 2b?
2a.
Yep, 2a again. So that tells us what we have to be between. Does 3 pi over 2 fit in the interval that I'm talking about? No. The highest you can go is pi over 2. This number is triple pi over 2. 3 times pi over 2. So it's too big. So in this case, the answer is no.
Are these formulas for next week?
Nope, these are new formulas for today.
Oh.
Yep. Okay, the next one is the sine of the inverse sine of 1.5. Okay, Ashley, this time the inverse is on the inside. Is that formula 2a or 2b?
2b.
Yep, that's 2b. Inverse is on the inside. So what two numbers do we have to be between?
Negative 1 and 1.
Yep, negative 1 and 1. Is that number between what you just said?
No.
No, so that won't work. Not only will it not even work, but if you type it in, it's going to say error. You won't even get back a different number than you started with, like you would have in the example above. Okay? This is impossible. Okay, and the last one. Inverse sine is still on the inside. So same restriction. Have to be between negative 1 and 1. So Ryan, will that example work?
Yes.
Yes, that will work. Okay, any questions on that? You know, the only other way you could see this question written is if I did something like this. The answer to that question is not yes. Okay? I'm asking you what the sine of the inverse sine of 0.6 is. So I'm looking for a numerical answer, 0.6. Okay? In this case, don't write yes. A lot of people on the test will write yes to something like that, and that doesn't make sense. So just read it carefully to see if it's a numerical answer or more of a yes, no, true, false kind of answer. I'll put it back the way we had it. Okay, and cosine. Okay, so for cosine we have two formulas, very similar. It's going to be formula 4a and 4b.
So why are they, why'd you jump to 4? Is there a reason or just?
Is there what?
Why'd you go to 4?
4? Oh, why did I don't know. That's what the book did. Yeah. So if you look these up in the book, these are the same numbers the book does use. Yeah. I don't know why they skipped 3. Okay, but if you look in your book, this formula is on page 184. All right, so this time inverse cosine of cosine, they will cancel each other out. And the answer you get is exactly what you start with, as long as x is between two values. What was our restriction from yesterday on cosine, or inverse cosine? Yep, 0 to 180. If you're doing it in radians, you're between 0 and pi. In degrees, it's 0 to 180. And then formula for b. Very similar to formula 2b, except instead of sine, now we're using cosine. Cosine of inverse cosine of x, those two functions cancel each other out because they're inverse functions. The answer you get is what you start with. And this again has to do with how high and low the graph of cosine goes. So let's graph cosine and see if we can figure out how high and low it goes. I'll leave sine there just to compare it. So that's sine in blue. Cosine is going to come up in red. Okay. How high and low does the cosine function go? Yep, 1 is the highest and the lowest? -1. So this 4b has the same restriction that formula 2b did. In fact, sine and cosine are almost the same function. What would you have to do with, say, the blue wave to change it into the red one? Move it, yeah, shift it which way? Yeah, you could shift it just a little bit to the left, or you could shift it a lot to the right. And next week, we're going to learn more about that. Okay, sine and cosine are basically the same graph, except one is just a horizontal shift, or we call that a phase shift of the other. But they're almost the same. Okay, so try a couple questions. Is the cosine of the inverse cosine of 0.95 equal to 0.95? So first, figure out which formula you're using. Look at the restriction. Then look at your argument and see if it fits in that restriction. All right, so how about Cassandra? Is this going to be formula 4a or 4b?
4b.
Yep, 4b. Good. What are we supposed to be between on that formula? Okay, are we? Yes. Yep. Good. So that will work fine. Let's look at the last one for cosine. We'll just do 2. The inverse cosine of the cosine of 210. I want to know if that will equal 210. Okay, Olivia, which one is this similar to? 4a or 4b?
4a.
Yep, this one is 4a. We're supposed to be between 0 and 180. Are we? No, so that won't work. If you type it in, you will get an answer back on the screen, but it'll be different than the one you started with. Okay, any questions on ones for cosine? Okay, so we got sine, we got cosine, and what other trig function do we use a lot? The 3 basic ones. Tangent. Okay, tangent's a little different. Okay, tangent doesn't like to be like everything else. Sine and cosine, both very similar. They have that nice wave pattern to them. Okay, let's start with our restriction for formula 6a. Hey, Jacob, do you remember yesterday what we had to be between for our inverse tangent?
Negative 90 and 90, but it can't be equal to
Perfect. Negative 90 and 90, but you can't equal negative 90 or 90. Okay, so that's our restriction on formula 6a. And then formula 6b, you get the tangent of the inverse tangent of x equals x. Just like the other two formulas, this has to do with how high and low the graph of tangent goes. Okay, well, let's look at tangent and see what it looks like. I'm going to get rid of sine and cosine, so Doesn't look too confusing. And type in tangent. It's definitely a pattern to tangent, but it's not a nice wave. And we decided to focus in on just that middle section, right in that area. How high and low does it look like that function is going? Yeah, infinite. Infinitely up and negative infinity down. So there's no restriction on this formula. It always works. You can go as high or as low as you want. Any questions on that one? So it's a little different. Tangent's a very different kind of function than sine and cosine. Sine and cosine are what we call continuous functions. You could put your pencil down on a piece of paper and you could trace it without ever picking up your pencil. Tangent's not. I'd have to trace one section, pick up my pencil, and trace another section. So tangent's what we call a discontinuous function. It has breaks in it. Okay, so I want to know if that would be true. The tangent of the inverse tangent of 30.4. Would that equal 30.4? Let's take a second, see if you can figure out which formula it is, and then look at the restriction. Okay, what do we think? Is that going to work? Yeah, that's formula 6b, and I said that can work for anything. Okay, let's check it on the calculator and make sure it works. Tangent of inverse tangent of 30.4. Okay, worked just fine. Most values here will work just fine unless you happen to try one of the values that's undefined. Actually, no, that one works fine too. I'm sorry. So yeah, this is negative infinity to infinity. Yep, no problems with that at all. All right. Any questions on that? That's the second half of 3.1. It's not too bad. All right, so we're going to finish up with 4.1 this week. Okay, we'll do part of it today and then part tomorrow. So in a trigonometry class, if there was like a list of like top 5 things that you're going to learn, right triangle trig would be one of the top 5 things you should leave the class somewhat understanding how to do. Okay, so it's a pretty important concept. And it's a big concept. You know, converting degrees to radians and radians to degrees, that's important, but that's kind of baby stuff, you know, really simple. This is a much bigger concept that's very important and has a lot of applications. Okay, so we're going to just start out with reviewing a few basic ideas. Okay, what is a right triangle? Okay, a right triangle is any triangle that has a 90-degree angle in it. Okay, the 2 shorter sides in the right triangle we call legs, and the long side, that's your hypotenuse. Okay, next thing is an acute angle. Okay, what's an acute angle? Yep, Andrea? Okay, so it's an angle less than 90. And there's actually one more part most people forget. You want to know what else it has to be? It has to be less than 90, but it also has to be, yeah? Right, it has to be greater than 0. Okay, we talked about negative angles, like negative 10. That's not acute. Okay, to be an acute angle, it's got to be greater than 0 and less than 90. And a lot of times when we talk about right triangles, there's a special formula that comes up having to do with all the sides. Does anybody know the name of the formula that connects all the sides in a right triangle? Yeah, the Pythagorean theorem. Okay, what is the Pythagorean theorem? Somebody explain to me what that is. I said it's a relationship between the sides in a right triangle. But can somebody be a little bit more specific than that? Yeah?
Do you mean like a squared plus b squared equals c squared? Or like...
Well, that's, if you just assign certain letters to certain sides, that's how most people try to remember it. But what's the idea behind what you just said? Say you don't use A, B, and C for sides.
To like find a side, like isn't that what it's used for?
Yep. It's used to find a side. And how do you use the formula? Let's say you don't have your sides labeled A, B, and C.
Isn't C usually the hypotenuse?
Okay, so you have a hypotenuse in there. Yep, Ashley?
You take the legs and you square them and then multiply them by each other to get to the hypotenuse.
You square the legs and you do what with them?
Multiply them. Oh, no, add them.
Add them, yeah.
To get the hypotenuse.
So you square one leg, you square the other leg, then you add them together, and that equals the hypotenuse squared. Whether you call your sides A, B, C, or X, Y, Z, doesn't matter. A lot of times we do use A, B, and C. If you're going to use A and B for your legs and C as your hypotenuse, that's what the Pythagorean theorem would look like. But it's important to remember the idea behind it, not just A squared plus B squared equals C squared. That doesn't mean much. Okay, any questions on the Pythagorean theorem? We're not going to go through the proof. There's actually a very simple geometric way to prove the Pythagorean theorem and show it's true, using nothing more than algebra 1 and area of squares. But we're not going to go through that. Okay, so what we're going to be doing is we're going to define our 6 trig functions, just like we did with unit circle trig. Except this time we're not going to define them in terms of a circle. We're going to define them in terms of a triangle. But before we can do that, there's 2 terms we need to understand what they mean. Okay, opposite and adjacent. Did anybody ever use these 2 terms in right triangle trig before? A couple people? Okay. Looking at this diagram, does anybody know what the opposite side would be? Based on the fact that I've labeled theta, the angle, as the lower right angle. Yep.
It's the side opposite from the angle, so it would be the one going up.
Yeah, the vertical side here, this would be opposite. Which side would be adjacent? Go ahead. Do you know, Rachel?
I think it's the side opposite from 90.
Well, the side opposite from 90, that always has a special name.
No, I think it's the one like going across.
The horizontal?
Yeah.
Yeah, that's adjacent. And this is hypotenuse. Okay, so the way we can remember it is that the opposite side in a triangle is the side that's farthest away from the angle, and it doesn't form the angle being referenced. Okay, in this case, I'm referencing theta. If you were to take away the opposite side in that picture, you'd still have an angle right there. Okay, because the opposite side doesn't make up any part of that angle. And then we also have adjacent. Okay, adjacent is the side in a triangle that does form one of the sides of the angle. And it's not the hypotenuse. Okay, so if I were to take away the adjacent side in this triangle, I would lose that angle. It wouldn't exist anymore. Let's look at another triangle. Okay, here's my right angle. And there's theta. Okay, which side is opposite in that picture? How about Michaela? What side would be opposite? At the bottom one. Good. Okay, how about Kayla? Which side would be adjacent this time? The one, so the long side or the other leg? The other leg, yeah. That would be adjacent. And the hypotenuse, that's always the side across from the 90. So what do opposite and adjacent depend on? Yeah, it depends on where theta is, where you put the angle. Okay, because it depends on something else's location. We call them relative terms. Okay, they're kind of like left and right. Okay, if I'm looking this way, left for me is towards the door and right is towards the windows. Okay, if I turn 90 degrees and now I'm looking at the windows, left is towards the back, right is towards the front, from your perspective. All right, so they depend on where you put theta. Okay. The hypotenuse is more of an absolute term. It's always across from the 90. It doesn't matter where you put theta. It's like me asking which direction is up. It doesn't matter if you're standing, which way you face. Up is always the same, but left and right are not. That's how these two terms work. So you've got to look where theta is, and then you can determine opposite and adjacent. Any questions on that? All right. So using those terms, we're going to define our 6 trig functions again. And this time we're not going to use a unit circle. We're going to use a triangle. Okay, we'll start with sine, cosine, and tangent. Okay, so sine is defined to be opposite over hypotenuse. Cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Now, when we did unit circle trig, what did we do with the 3 trig functions that are on the left to get the 3 that are on the right? Oh, we did, yeah, go ahead, Evan.
We did the inverse.
Can you explain what we mean by that?
Like we flip them.
Flip them, yeah. We found the reciprocal. Yeah. Yep. So cosecant is hypotenuse divided by opposite. Hey, Justin, what would the secant be?
Want to be the hypotenuse over adjacent?
Yep. Hypotenuse over adjacent. And Ryan, the cotangent?
Adjacent over opposite.
Adjacent over opposite. So if you can remember the first 3, then the last 3 aren't that bad. You just have to find the reciprocals. There's a trick or a word that some people use to try to remember the first 3. Anybody know? Sakatoa. How do you spell that? Yeah. Spelling it is key to using it. Yep. TOA. Okay. And what is in the SOH? What do they stand for? Yep. So sine is opposite over hypotenuse, and then the CAH. Cosine, and then tangent is opposite over adjacent. Okay, so it gives you, if that helps, it gives you a way to remember it by reading down. Don't read across, otherwise you get ipiodiapta. That doesn't make much sense.
Or you can read Sakatoa.
Yeah, Sakatoa, and then reading down is the way you remember what the ratio is. Okay, so Sakatoa. Okay, I had somebody once that tried to use Sacagawea, That doesn't quite work. That's somebody who helped Lewis and Clark. That's not anything to do with trig. So Sakatoa, not Sacagawea. So it looks like that these definitions are different than what we learned before. Okay, before when we did it, does anybody remember what sine was equal to?
Y over X.
That was tangent. Okay, tangent was y over x.
Sine is y.
Yep, sine was y. And what was cosine?
X.
X. Okay, I'm going to show you that these are exactly the same thing. There's no difference between what I'm showing you right now and what you've already done. Okay, here's a unit circle. There's a triangle. Let's call the bottom side x, call the height y. In a unit circle, the hypotenuse is 1. And put theta right there. So these were our unit circle definitions. Okay, let's use our new definitions and see what happens. It says sine is opposite divided by hypotenuse. What's the side opposite theta? Y. Divided by, what's the hypotenuse? 1. So it's exactly the same as what we had before. Okay. Cosine, our new definition, says adjacent over hypotenuse. What side is adjacent to theta?
X.
Yeah, x, and the hypotenuse is 1. Divided by 1, same thing. And then tangent is opposite over adjacent. The side opposite is y. The side adjacent is x. So these 6 definitions really are the same thing you've already done with unit circle. We're just calling them, instead of x's and y's, we're calling them opposite and adjacent and hypotenuse. Any question on that? All right. So let's use our 6 definitions to find all the trig functions I have up here. Okay, before we can find the trig functions, there is something we should do because we're missing something. Okay, what are we missing? Yeah, we're missing the hypotenuse. And if you don't have that, you can't do the sine, the cosecant, the cosine, or the secant. Tangent and cotangent we could do.
So just do Pythagorean theorem.
Yeah, so that's what we should do. Do the Pythagorean theorem. 3 squared plus 4 squared, if you call your hypotenuse c, it equals c squared. Okay, 3 squared is how much? 9. And 4 squared? And what's 9 plus 16? 25. So what would c be? 5. Okay. Now we know what that is. Now we can fill these in. So Montana, what's our definition for sine? We divide what, 2 sides?
Opposite over hypotenuse.
Yep, opposite over hypotenuse. What side is opposite here?
4.
Good. What side is the hypotenuse?
5.
5. Done. That's it. That's the sine. Okay, cosine. Jacob, what would that be?
Adjacent over hypotenuse.
Adjacent over hypotenuse. So in this case, we would have,
3 over 5.
good, 3 over 5. And Michaela, my tangent would be, okay, start with the, what's the definition of tangent? What over what? Opposite over adjacent. Okay, so what side is opposite theta? 4. What side is adjacent to theta? 3. Okay, so there's our sine, our cosine, and our tangent. Emma, what would the cosecant be? 5 over 4. Good. Okay, Cassandra, the secant? How'd you get that? How'd you get 5 over 3? So when you said 5 over 3, you are right. But how did you do that? Flipped. Yes, you flipped the cosine. 5 over 3. And the cotangent, I'll do that one, it's 3 over 4. Okay, knowing that we have a right triangle here, any one of these 6 pieces of information is enough to find out how big that angle is. One of the first 3 would be the easiest to work with, but I could find how big theta is, in degrees or radians. I'm not going to do that today, but that's what we'll get into more tomorrow. Next thing is complementary angles. What are complementary angles? Emma? What'd you say? Angles that?
I was being sarcastic.
Oh. Does anybody know what complementary angles are?
Isn't it two angles that are the same?
Those would be congruent angles. 2 angles that are the same, congruent.
Don't do it.
This is close, but complementary is a little different.
Are they next to each other?
Next to each other means adjacent. Okay, so 2 angles that are next to each other share a vertex and a side, or adjacent. So there's not too many more terms for angles. Yeah? Brian?
Do they equal 180 complementary angles?
Um,
Or is that-
well, the angles that add to 180
Yeah.
are supplementary. So we're getting close. Yeah, Andrea?
Angles that add up to 90.
2 angles that add up to 90. Okay, so complementary angles add up to 90. So my next statement is the 2 acute angles, 2 small angles in a right triangle are always complementary. 2 acute angles in a right triangle are always going to be complementary. Why? Why does that have to happen? Montana?
All the angles in a triangle add up to 180, so.
Yep, we didn't say that yet, but that's true. All the angles have to add up to 180. Go ahead.
So the 90 plus the other 2 would have to be 90.
Right. Okay, you've already used 90 for the right angle, so you've got 90 left over split between the other 2. So they have to be complementary. If they weren't, they wouldn't add up to 180. Okay, we're going to take the idea of complementary angles and we're going to combine it with the idea of cofunctions. So cofunctions are just another way to pair up trig functions. Pretty much up until now, I've had you guys pair them up as reciprocals. You flip one to get the other. Flip sine to get cosecant. Flip cosine to get secant. Flip tangent to get cotangent. Okay. Cofunctions are a little different. Okay, we start with a trig function, and then we put the word co in front of it to find its cofunction. So sine, and what do you think the cofunction would be for sine? What is it? Cosine, yeah. Sine and cosine are what we call cofunctions. That's the first pairing of cofunctions. So we say that the cofunction for sine is cosine. What about the cofunction for cosine? It would be sine. It's not cocosine. It goes back to sine. Okay, and then the next one, we have secant. What would be the cofunction for secant? Cosecant. And then the cofunction for cosecant would be secant. That's the second pairing of cofunctions. And the last one happens to be the same as the reciprocal as well. Tangent and cotangent. Any questions on those pairings? That's it. Those pairings, they're just called cofunctions. All right. So we're going to take a look at this right triangle, and we're going to just write down a couple of the trig ratios. And maybe you'll notice a pattern. Let's start by finding the sine of alpha. Okay, so it's not going to be numbers, it's going to be all letters. We always label our sides A, B, and C. That's usually the way you do it in the Pythagorean theorem, so I've used that Same idea here. But how about these letters that I used for the angles? What kind of letters are those? They're Greek letters. Yep. We're always going to use Greek letters to represent angles. Anybody know the name of that Greek letter?
Oh,
Yep, alpha. And how about that one?
beta.
That's beta. The reason we use Greek letters to represent the angles is because some books will use lowercase letters for sides and then capital letters for angles. I think that's confusing. Because then if I say to you, what's A? Then you have to clarify it. Do you mean lowercase a or capital A? We're not going to be using lowercases and capitals. We'll just use English letters for the sides, Greek letters for the angles. So if I'm asking you for a Greek letter, you know it's an angle. All right, so let's find the sine of alpha. So sine is opposite over hypotenuse. Yeah, Ryan?
A over C.
A over C. Now I'm going to find the cosine of beta. Let's see what that comes out to. So cosine is adjacent over hypotenuse. Anybody think they know what the cosine of beta would be?
A over C.
Yep, go ahead, Aaron.
A over C.
So let's check. Cosine means adjacent over hypotenuse.
Oh,
So what side is adjacent to beta?
A.
Yeah, A. And the hypotenuse?
C.
C, that part was fine. Okay, what do you notice about the cosine of beta and the sine of alpha? No, they're not reciprocals. Yeah, they're exactly the same. They came out exactly the same. Let's try another one. Let's do tangent of alpha. So tangent is opposite over adjacent. What's the tangent of alpha?
A over B.
Yep, A over B. And anybody have an idea what I'm going to ask for next? Yep, I'm going to ask for the cotangent of beta. So cotangent, tangent is opposite over adjacent, cotangent is adjacent over opposite.
B over
So what's the side adjacent? Remember, we're switching our perspective now. We're going from beta. It's A over B again. It came out the same. Tangent of alpha and the cotangent of beta. Okay, let's look at what's happening. Sine, cosine. What are those called?
Cofunction.
They're cofunctions. Alpha and beta. They're two angles, but what's the relationship between alpha and beta? They're complementary. Let's look at the next one. Tangent, cotangent. Are those cofunctions? Yep. And then alpha and beta are complementary. Right? So we have this pattern here where if you have cofunctions and you're working with angles that are complementary, you end up with the same answer. And that's the complementary angle theorem. It's very simply what I just said. If you have cofunctions and you have angles that are complementary, the answers that you get are the same. They're equal. Cofunctions of complementary angles are equal. Okay, so we'll look at three kind of simple problems, and then that'll lead into what our example will actually be. Okay, the first one says the sine of 30. Using the complementary angle theorem, I want something that would be the same as sine of 30. Yep.
Would be the cosine of 60.
Yes, the cosine of 60. Why? Sine and cosine are cofunctions. 30 and 60 are complementary. So you pick the cofunction and then you pick the complement. and you get something that's equivalent. Okay, what about the next one? Tangent of 15. Montana?
Cotangent of 75.
Right. Pick the cofunction, then pick the complement. Okay, and last one before we try our real example, secant of 40. What would that be the same as? Well, Monique? What would that be the same as? Okay, well, start with what's your cofunction of secant? Okay, so here's our pairings. What's the cofunction of secant?
I just don't understand.
So these sine and cosine, that's one pair of cofunctions. Tangent and cotangent, that's another pair of cofunctions. And then there's this pair, which is the one I'm asking about.
So then CSC, but
You want to tell her, how do you pronounce CSC?
I don't know.
Cosecant. Okay, cosecant. So secant of 40 is going to be the same as the cosecant of, do you know what number goes here? What do you notice when you add up 30 and 60?
They have 90, so it'd be 50.
You have to add up to 90. You have to work with angles that are complementary. Okay? So here's an example where you would actually use this idea. Okay, we have the negative sine of 15 divided by the cosine of 75. Yeah, just forget about the negative for 1 second. Just pretend it was sine 15 divided by cosine 75. What do you notice about those two things? The sine of 15 and the cosine of 75. Okay, the angles add up to 90. Yep. What about the functions? They're cofunctions. So we have cofunctions of complementary angles. What does that mean about the sine of 15 and the cosine of 75? They're equal. We're dividing two things that are equal. And we also have a negative in front. So what do you get when you divide two things that are equal and then put a negative in front? Andrea? Yeah, -1. Okay. I have no idea what the sine of 15 is. I have no idea what the cosine of 75 is. There's some long decimals. But I do know that they're the same because of this theorem. Whenever I divide two things that are the same, I always get 1. And in this case, I have a negative in front, so that makes it -1. Okay, let's try another one. The tangent of 12 minus the cotangent of 78. Okay, any thought what that one's going to come out to? Montana?
0.
Yeah, 0. Can you explain why?
Because they're equal, so.
They're equal. And when you subtract two things that are equal, you always get 0. Doesn't matter what they are. They're equal. So we know we're going to get 0. Any question on that? If you change this 78 to a 77, then that throws out the whole idea. You can't do the problem in your head. They had to add up to 90, and they had to be cofunctions. So this idea we can do with division, we can do with subtraction. How about addition? If I add two things that are the same, do I always get the same answer? No. So this wouldn't work with addition. When you add two things that are the same, you get the answer doubled. So we can't use this idea with addition. How about multiplication? No. If you multiply two things that are the same, you get that thing squared. Okay, so you can't do this with multiplication either. Only subtraction and division. Okay, so on the test, the problems will look something very similar to this. I could do something like that, which would just mean 0 plus 5, which the answer would now be 5. Okay, so the point here is to try to take something that looks complicated and make the arithmetic much easier than it looks. Okay, any question on that? All right, so I think that's a good place to stop. Okay, so on 187, that's all the true, false, yes, no kind of questions. So it's 46 to 51 and 53 to 55 all. And then page 255, that's the right triangle trig. 9 to 21, just the odds. Okay, just the odds on that part.